Chris is the market and business strategy lead for the FLARE technology at Labsphere. He's served the remote sensing space and aerospace communities for over 25 years for Labsphere. He's played many roles, including product development, sales, marketing, and executive leadership. He currently is the liaison to NASA, ESA, and other space agencies for radiometric solutions, master calibration, and test systems. Chris has helped to specify, design, and implement many spacecraft calibration solutions with industry satellite providers such as Raytheon, Harris, Lockheed Martin, Airbus, and many others. He designed and implemented Labsphere's flagship calibration product line called Helios. He was the originator and is the current secretary of the IEEE P4001 Committee for Hyperspectral Standardization, with a team of over 260 global leaders engaged in creating testing, terminology, and data standards for this remote sensing technology. Finally, Chris also works closely with global national measurement institutes like NIST, NPL, and PTB to ensure that Labsphere's traceability is at world-class standards and to ensure the highest caliber of products for its customers. So it's a very impressive career that Chris is having. And so with that, I'll just say that as far as questions, what we've been doing is encouraging people to type their questions in on the Zoom chat function. And I think Chris and his colleague, Brandon, will try to keep track of those during the talk and then present the answers afterwards. So if we can all keep ourselves on mute during the talk, we'd appreciate that. And David and I will be looking to mute people who haven't muted themselves. So don't be offended if we do that to you. Chris, you're on. You can share your screen and go for it.
Very good. Well, thank you, Peter, for the introduction. And, you know, it's always easy to do when you write your own intro to make yourself sound super impressive. But
thank you for writing it.
All right. Let me see here. We got a screen coming up.
Yep.
All right. Let me go to full screen on the presentation. Okay. So I like to point people to Dr. Brandon Russell is here with me tonight, and Brandon's our science lead for FLARE. His background in oceanography and ocean color, remote sensing, hyper, etc., and tremendous asset to Labsphere. And he is volunteered kindly to monitor the chat and answer as many questions as he can. So I can roll along and get you guys as much information as we can about calibration for Earth satellite imagery. Please feel free to put those questions in the chat, and Brandon's been absolutely.
I'll be answering them as they come in, and if there's anything that I can't answer or that you'd like more information for, both of our contact info should be in the slide. Please feel free to just shoot us an email.
Right.
We'll see what we can do.
Right. Thanks, Brandon, for doing that. And this talk goes for about 45 minutes, just for everybody's timing purposes. I will try to keep it rolling along. There's a lot of information here. I apologize. I do speak quickly. So I'm going to try to cover a lot of ground here. Specifically, I'll do 2 minutes on who Labsphere is, for those of you that don't know, and then we're going to dive right into what is the market for satellite and remote sensing and electro-optic calibration, give you a technical overview of a new tool we're bringing into this space that we think can help a lot, called FLARE, and what you can do with it, and then we'll finish up with talking about analysis-ready data and data value. Labsphere is, we are experts in the science of light, primarily radiometry, if it has to do with measuring or characterizing. We do, a lot of our work is traceable to NIST. We're NVLAP accredited, which means we're directly audited by NIST. We live in the absolute world. So as I talk, just remember, I'm always talking from an absolute perspective. When you work in the relative world, things get a little bit easier, but in the absolute world, we always are traceable back to a National Measurement Institute, NMI. We're based up in the Dartmouth Lake Sunapee region, so we're local. I've been up there for about 40 years. I've been with them for 25 of those 40 years, and it's a great place to work, really dynamic environment. We do a lot of different things. Image sensor tests and remote sensing are kind of what I'm focused on. And the differentiation between those two things is remote sensing is really the science instruments that are doing the image capture. And image sensor test is more like your cell phone or other types of sort of commercial imagery, machine vision, et cetera. A little bit different parameters in terms of the absolute performance between those two things. That's the separation. We measure light with our with our instrumentation, and we also produce some of the world's best reflective coatings, diffusely reflective coatings. We're also doing a lot of work these days with autonomous vehicles because of LiDAR and augmented virtual reality. Kind of have our fingers in everything, which makes it really fun place to work. What we're really well known for in this space is satellite imager calibrators. In the last 40 years, Labsphere has designed about 95% plus of the world's ground-based calibrators. If it's been launched and it images the Earth, one of these has come from us at some level to provide some ground truth to those satellites. So before they launch it, they want to characterize it with something that can produce the radiance of the sun all the way to the full darkness of the Earth. And we produce these systems. The one on the left is for Landsat 8 and 9, which are currently the moniker satellites in the US fleet, best satellite in the world, some would contend, for radiometric performance and calibration. And Landsat 9 will be going up in September, hopefully equaling or bettering its performance. So we're really looking forward to that. And then on the right is the big brother of that one. That's a 2-meter sphere with a 1.5-meter aperture for a spaceborne telescope that's going up from India. So a lot of design that goes into these types of things. Each one of them is a little bit unique, designed around the instrument in question. Spectral is also something else that we're well known for. It's the whitest material on the planet. We can cut it into all sorts of shapes. What you see, the highest common usage is to use it as a target for remote sensing, which we'll talk a lot more about in the coming slides. It can be used for hundreds of different applications, so from blood analysis to a reflectance standard to door openers. So we utilize it in a lot of different spaces. If you need something really, really white, or you need something with a grayscale in it or a color, it's like titanium white. We can dope it with different materials. So lots and lots of uses for that. And we take that same spectral material, and this is a timeline for the amount of satellites that we have assisted in terms of creating the fundamental calibration equipment that are on those satellites. And that takes usually one of two forms. It takes either the form of a target that gets flipped out into space as an absolute white reference to baseline against the solar exoatmospheric radiation, or it actually is a small integrating sphere or system inside in the satellite that actually has a lamp or an LED or a laser in it that provides a baseline that the satellite can kind of turn on and off at will for baselining the satellite. We're on our 19th satellite very shortly going up. You can see that also, for those of you familiar with this industry, these are the premier satellites on the Earth, the A-Train for NASA, ESA, JAXA, all the space agencies around the world. We provided this level of calibration and service and fiducial reference for these satellites, and we're very proud of that work. So without further ado, let's jump right into satellite and remote sensing market. Let me just give you a sense of what's going on there if you haven't been watching. This is the global space economy at a glance, and my source here, if you want to do more research, great location, bricetech.com. It's a $366 billion space economy. We are not serving all of that here. We're serving a very small section of it. Specifically, remote sensing is what I'm going to be talking about today. It's a $2.3 billion market, much smaller, but still very, very lucrative for little old Labsphere. The global space economy includes everything from GPS to communication satellites to television and so on and so forth like that. So and the military, and so it's a much bigger market than one we're serving here. Very active market. If you haven't heard about it in the news, the amount of satellites being launched year by year has gone up exponentially. In fact, actually this past year, 2020, 85 satellites were launched. That's compared to the past 50 years, where used to be kind of a couple, a dozen, maybe on a really heavy year got launched. Now we're putting these things up on an every week type basis. That's to create largely things like global internet and huge communication networks and some of these other innovations that people have come up with. But a very large portion of that is actually remote sensing. So 50% of the launches, this is 2019, but 50% of the launches in 2019 of 386 satellites, 50% of them were remote sensing oriented. That is a lot of satellites looking down at the Earth, trying to create lots of value in the data products. And that is what we'll be talking about mostly tonight. In the data products themselves, the trending that we see going on right now, and this is from some publicly available information here at this link, it's Samarasense, a very nice little company making these small sats. The trend is towards high resolution, high accuracy data. The demand for this is going up exponentially. There's also a lot of demand for kind of medium resolution data, but imaging the Earth every day, every hour. But the data value to those customers is quite a bit different in terms of people pay low dollars for this, they pay high dollars for this. So there's an explosion tending towards the high accuracy, high resolution side of the equation. Although a lot of the sats that get launched are still kind of 3-meter resolution or so. I'm primarily going to talk about some of the technology we're going to talk about really has an influence on this left side of the target of the graph here. Let me change this pointer to a laser pointer just so it's a little more visible. Okay. From the government perspective, the government is the single largest buyer of commercial data, commercial satellite data. This is just a timeline from the recent NGA Industry Day back in November of last year. You can see that in the past, we have the U2 sort of flying out there by itself in terms of high resolution data and products, and that's certainly a product that's well known and maintained here in the East Coast. But as we go forward into the present, we have a lot more assets available at our demand, a lot more data products available to us, and a lot more intelligence to derive from that. And in the future, that's really going to explode, and we're going to get into linked networks and much deeper knowledge sets, real-time information, and that is due to the explosion of these satellite launchers. Just to give you an idea of the commercial remote sensing, the number of satellites that have gone up, that are up there currently, 2020 has 451 satellites, specifically in commercial remote sensing. And that includes both electro-optical, which is what I'm going to focus on in this talk, and radio frequency or SAR, as well as other types of things. So the blue sector, you see the US owns the market right now, but as we go forward in time, 10 years, we're not only going to have an explosion of more satellites up there, but also the space is going to be very contested. The rest of the world is catching up and catching up fast. Every single nation on the planet is basically developing its own remote sensing or its own satellite program in the new space race that we are in today. So it's an exciting market, it's a very dynamic market, and it's a market that needs some solutions, and we're going to talk about that. For remote sensing calibration, this is normally a full day talk that I give, if not multiple days, but I'm going to try to condense that into about 10 minutes for you. At least give you some snapshot of what remote sensing calibration is about today. And then I'm going to talk about how we can augment that going forward. So I'm going to talk about reflective remote sensing. This reflective remote sensing is basically, I have a source, I have a target, and the light is going to hit that target, and I have a sensor somewhere that's going to receive the light from that target. That target is reflecting light. There are two basic types. There's passive and active. Active is more, we have control of the source as part of this equation. So that's like LiDAR, sonar, radar. We emit something at the target reflects, and we get it back to the sensor. So there's two aspects. There's the modulation from the source, and there's also the modulation received from the target. And you can derive some really interesting information from that. That is SAR and radar. We're going to be primarily in this talk dealing with passive remote sensing. We don't have control of the source. The source is most typically something like the sun or some other light source that we do not actively manage or mitigate. It just we're looking at the target, we have to deal with the source that we're dealt with. So that's what's called passive remote sensing. And again, I'll give you a disclaimer that I always talk in terms of absolute measurements here. So just always keep that in mind as I sort of talk about what things are hard and what things are not. So Lambertian targets are what are used today as a primary calibration source for satellite imaging. You go out to the field, you take a diffuse target with you, something like a tarp, a large piece of cloth that's very diffuse, or you take a piece of spectral on with you, and you then proceed to try to measure everything that's going on in the environment, including the direct solar component, the sun shining on the target, but also the indirect. The atmosphere is also reflecting light back onto the target. And we also need to know something about the atmospheric path that is going between the sun and the target and the target and the satellite itself. And then if we're not careful with the target, we become part of the measurement because we're reflecting, or we put it too close to something, and then we have adjacency effects and other things. But in a campaign for calibration, the target plays the central role of providing the ground truth for the measurement. And if everything around it has to be measured and quantified. So this is, if you've ever been on one of these types of calibration campaigns, they are a dance of usually about a dozen people running around the field with instruments strapped to their backs, trying to measure spectral on and then trying to measure what's surrounding it. So here on the left, we see some different diffuse targets of different reflectivities. These are tarps and solid targets that have been put out. There's a piece of spectral on right here. You see our friend is pointing his ASD spectrometer at this, trying to get a baseline on that spectrometer before he then goes and marches around. This is my friend Mark Helmlinger, works for JPL, does a lot of the baseline calibration out at Railroad Valley Playa, which is in the middle of nowhere in Nevada, about 8 hours from anything. And Mark will measure this target and then proceed to walk a 2-mile circuit around this dry alkali lake bed, which is a very white, very bright, diffuse uniform target, which is used for a lot of satellite imagery today as a baseline for their reference. So, but Mark has to measure up, he has to measure down, he has to measure BRDF, which is a scattering profile. A lot of measurements have to be done. Mark usually goes out there with a team of probably no less than 6 to 12 people, depending on what he's trying to do. So really arduous, hundreds of thousands of dollars for these campaigns, and they can take several weeks. And if the weather isn't good, you can come back with absolutely bupkis of measurements. That's a technical term, by the way. So we need good atmosphere. Atmosphere is the #1 enemy of this type of work. It also is the thing that we're trying to remove from our measurement when we're taking images. The atmosphere is a distorting media. Over short distances, you can ignore it. If you're doing drone measurements or you're taking pictures with your cell phone, atmosphere really doesn't play into it unless you have really strong absorption, like a heavy fog or smoke or something else that might act as a disruptor from the atmospheric perspective. But when you get to longer distances, airborne satellite measurements for sure, you are ignoring the atmosphere at your own peril. And in fact, you're actually imperiling your data. There are some tools you can use to uptake on this. There's a company here in Burlington, Spectral Sciences. They make a great product called ModTran. ModTran allows you to sort of predict the atmosphere if you know where you are on the Earth and what day it is. And you can basically emulate the atmosphere using the ModTran product, but it's a model. It's an emulation. It's not actually a measurement. When you do ground truth like this, you actually need to measure the atmosphere while you're doing it. It's very important that you do that. And then you can use ModTran to help clean that up. And I'll give you a quantitative example of that. So this is from our friends at the South Dakota State University Image Processing Lab. These are guys that 24/7 do remote sensing calibration for a lot of the satellites out there. So this is I borrowed this from one of their presentations because it's a really great example of some of the image processing levels and some of the impact that good measurements can have on the ground. So you see on the left, we have no atmospheric correction at all. This is just raw satellite imagery that's been orthorectified and uniformly corrected. But I would say uncertainty is probably in the neighborhood of around 20%. The atmosphere is a scattering media for a variety of reasons: aerosols, Rayleigh scattering, etc. It's also an absorptive media, so there's a lot of things going on in this image that really lead to a lot of uncertainty in the measurement. If we take ModTran and we model out that atmosphere, we get a lot better, factor 2. and that provides a lot more fidelity to the image. We're getting closer to the actual surface reflectance. But then if we have somebody on the ground who was doing those ground campaign measurements using a piece of Spectral or some other reference to do the measurement, then now all of a sudden we can get to the fidelity that we really need to do science, which is sub 3%. Now, sub 3% happens to also be about the best in the world at this time. That's where NASA is. It's where the space agencies, when they go out to a field campaign, if they can get 3%, it's a really good campaign and they all go home and drink a beer. But if, for the most part, 3 to 7% is kind of what you get for a field campaign, but it dramatically improves your image quality if you can get to this level and get to the surface reflectance. And surface reflectance is really what we're after, because that's where the data is. If you're not an atmospheric guy, if you're an atmospheric guy, the data is in the atmosphere, but we won't go there. This is just to give an example of what SDSU uses to baseline that. So there's a variety of things that are laid out here. You see some mirror targets, which we'll be talking a lot about. You see some, just for reference, this is 2 trucks over here. This is a big target, a couple 100 meters, 20-meter targets down here, a black one and a white one, and those are actually going to be used for spatial or geometric validation as well. What you don't see, because of the resolution of this image, this is the fleet of grad students running around in the field here making measurements while the satellite is going over to provide the ground truth to that measurement. It's very arduous. And again, weather in South Dakota is not always perfect. So when they get a good day like this, it's all hands on deck and they're out running around in the field taking measurements. Quite a ballet. I'll point these 2 targets out again, black and white. That gives us also some geometric references. An edge method is the most common method for geometric evaluation of the satellite performance. That's its focusing ability, its image quality. So if we have a high contrast target with a sharp line, black and white, then we get some blur here, and that blurring is from the pixel response associated with going from a high contrast to a low contrast. And that transformation gives us some idea of the image sharpness or image quality. If you don't understand these surfaces well, then you can introduce a lot of noise. Also, the edge has to be at just the right angle to be able to get the type of phasing that we want in the pixels to be able to get that image quality evaluation. So there's some issues with this, but it is the method that people use today to do this type of measurement. And they also do use line methods. If you have a high resolution satellite, maybe they'll use bridges or roads or airport runways, known man-made straight lines. They can give you some edges or give you some lines. We can also use mirrors to do this, and you'll see some examples of that coming up. Again, you have to be directional with this. So you got to have just the right set of angles. Usually what they'll do is they'll find some good edges and some good lines, and they'll try to statistically beat those down by building a lot of images and statistically getting a higher sampling rate on a variety of different targets to really try to beat down the noise that they get from these 2 different methods. Versus what I'm going to be talking about for the rest of this talk is point methodologies. So a man-made point source, natural point sources are really hard to find, but a man-made point source using the flare technology, which I'm going to be talking about, provides an omnidirectional source. There's no directionality to this. We can get the same quality of information from this impulse response that we can get from an edge or a line method. We do potentially need more than one point source to develop good statistics on it, but that also gives you a ground control point as well, because we know exactly where that position is located. So that gives you some rectification and some location on the ground. So that's what's done today. I'm not proposing that we are displacing any of that technology. In fact, those are the methods that we're trying to compare ourselves to. But I want to talk now about FLARE, which is a new technology that we're bringing forward that the community is very excited about in terms of how FLARE works, what it is, and what it could bring to the community in terms of a new tool and a new way to do image analysis on a totally different scale of cost and real-time calibration. So, as I've mentioned already in the previous slides, Vicarious calibration today, there's some room for improvement. There's some problems there that could be tackled. First problem is that people don't calibrate, which sounds shocking. You would think that if you're going to spend all this money to launch a satellite into space, that you would take great pains to make sure that it's doing what you think it's doing. But in a lot of ways, if I'm trying to count the cars in the Target parking lot or the Best Buy parking lot, calibration is not that important. Resolution's important, but I still should be trying to take more calibration than they're doing today. And the reason why they don't calibrate more is because it's difficult. Those campaigns I just detailed, they require expert knowledge. It takes a lot of time. You got to do it right. It can lead to a lot of inconsistency if you do them wrong. And generally, the only people that have the wherewithal and the fortitude and the capability to do these types of calibrations are the national agencies like NASA and the government and the space agencies around the world. You got to have some high cost assets, both in terms of people and equipment, to be able to do these well. So these calibrations are not done frequently. And it really is a problem in trying to get to higher sensor fidelity, or harmonization is another way to think about it. If your satellite is calibrated one way and another satellite is calibrated a different way, how do you know those two things are actually going to match up to each other? How can you harmonize the imagery from one satellite to another satellite? So there's a sensor to sensor mismatch within a constellation because of the inconsistency and the infrequency of calibration. And then let alone also, if I'm trying to go from space to airborne or from low resolution to very, very high resolution, really hard to harmonize that whole chain of calibration with a single methodology like the one that we showed with the campaigns in the desert and so forth. You can do TARPs and targets and things like that, but again, there's room for improvement there. Additionally, the atmosphere is not our friend. It's not constant. It's hard to measure in real time. So you got to really do that well. Large targets just up here in the upper right are often misused. So in this image, we can see 4 targets that have been deployed, but do I have enough pixels on each one of these targets to actually say that every target is actually giving me a calibrated reading? And just from this image, visually, I would say no. There's probably not enough. There's too much adjacency here. These pixels are affecting these pixels over here and vice versa all the way down the chain. So there may not be good pixels in this image. There's also no single method from space to airborne convergence. And then spatially, people use, as I mentioned, they've got to find edges. So you got to find bridges and roads, or if you're a large sensor, a 300-meter pixel, you got to find a coastline or something. And you can see here from this coastline example, we're looking for this red function. And what we're getting is something that is not very edgy. It has an edge, it has a function, but I'm really going to have to get a lot of coastline images to really beat down the noise in that signal to figure out what my actual image resolution is from that natural target. So are natural Lambertian targets the right way to go is a question I would pose. Now, we love Lambertian-like targets. I just went on about Spectral on. We're not saying that you shouldn't use that. In fact, you should continue to use this as a fundamental reference. But again, as I detailed before, there's a lot of things you have to do to get this right. All these things have to be measured and accounted for in order to understand what the actual radiance of this target is. So what I'd really like to do is I'd like to maybe just relay the sun, which is a really well understood, really constant, very well calibrated source. I might want to just relay the sun to the satellite using a specular reflectance, because then I only care about one path. And in that particular case, there's also some other derivative benefits I might get from this. And here we're going to talk about the SPARC methodology, which was developed by Raytheon, another local company. Labsphere has licensed the SPARC method, and I'll talk a bit more about that on the next slide. But very simply, the idea is if I can take the sun, which again is a well-calibrated, or at least well-measured source, a very stable source, and I have a specular target that just relays that to the satellite, then all I care about is this direct solar path between the sun and the mirror and the satellite. Now I do care about the background too. I want a nice dark background, or a background that doesn't offer a lot of noise to my signal. But if I can do that, I know what the sun is doing, and I can deduce that from what the satellite response gives me. Additionally, if I choose the right mirror and it's small sub-pixel, now I've created an artificial or a man-made synthetic point source, which now gives me an impulse function that gives me some spatial information about how the imager is actually seeing this impulse function. And it gives me a ground control point. And all of the energy in that little target. Now this is a little tiny target instead of a big tarp. This little tiny target gives me all the information I need just in this single pixel. So if I took a flat mirror and I tried to do that, the problem is that this is moving, the sun is moving, the earth is moving, and the satellite is moving really fast. So I have a bullet with a bullet problem. I'm trying to take this bullet and hit this bullet over here with that. So my tracking system down here has to be really robust and very agile to be able to hit the bullet with the bullet problem. So instead of using a flat mirror, I'm going to use a curved mirror, a spherical convex mirror. So that buys us a lot of things. Number one is it offers us an angular field of regard. The curvature of the mirror actually spreads the energy out over this field of regard between these two blue lines. So if we catch the satellite or the satellite flies through this arc, we look like a constant point source anywhere in here. So if it takes an image anywhere in this arc, it actually is seeing a constant radiant point source, which is proportional to the sun. I say proportional because the arc also spreads the energy out over a subtense. So it acts like an ND filter. The radius of curvature acts like an ND filter. That drops the signal. So if I just relayed the sun with a flat mirror to the satellite and I was able to hit it, I wouldn't do anything except for saturate the satellite or perhaps even damage the satellite. The sun is pretty bright. So I want to lower the signal to the sun by using a smaller mirror. That's the aperture stop. So the size of the mirror gives us an aperture stop and limits the amount of signal that can be returned to the satellite. And then the radius of curvature further reduces that by spreading the energy out over an angular subtense. So the curved mirror gives us attenuation. It gives us a field of regard that makes this tracking problem much less arduous because now maybe I have 5 or 6 degrees that I can hit the target with instead of the 0.1 degree that the sun actually subtends. So much easier to hit that target. But I also need a third piece here, which is I need a solar radiometer. I need something that's actually measuring the sun and the atmosphere at the same time so that I can then use this to predict the radiance the satellite actually sees. The other nice thing with the mirror technology is that one mirror equals signal 1, but if I actually am able to couple together a number of mirrors of the same size and the same radius of curvature, 9 mirrors equals signal 9. So it's directly linear and proportional to the number of mirrors that I deploy, as long as they are sub-pixel. This is a completely linear scale that I can develop using these mirror target arrays. So I'll show you what that looks like from space. This is the Iconos, and this is some testing that was done in Raytheon's parking lot. You can see that I have a variety of SPARC targets here, and the satellite is going over in the field of regard, that angular subtense where the mirrors appear to be on. And then the image here on the right is the satellite has gone 1 degree outside of the field of view, outside of the field of regard, and they are off. So there's a really also a very nice on-off capability here that we can do just by simply dithering the mirrors in a small angular subtense. So that offers some other exciting possibilities. I won't dive into that, but the other thing I want to point out here too is that these look pretty much the same to the naked eye, but actually what's going on here is you can see proportionally, each one of these mirror targets is sub-pixel. They all look like a point source, but there are different numbers of mirrors applied to each of those point sources. And we see directly spectrally independent proportional signal to the number of mirrors that are deployed in each of these targets. So not only am I getting radiometric information and spatial information, I'm also getting linearity evaluation of the satellite's performance in a single image. Pretty powerful, pretty impressive. I'm going to show you how the flare systems actually work. They take the SPARC mirrors and they actually deploy them into a azimuth and elevation turret and a radiometric tower. And we're going to measure here the solar radiance, the atmospheric transmission, the background, the mirrors, and then we're going to relay the satellite, the sun to the satellite. So first, my radiometric tower measures the sun and the atmosphere. It measures the mirror reflectance and it measures the background. It's an articulated tower that does that. The energy from the sun, the mirror targets the sun, and then it tracks the satellite by relaying the sun to the satellite. That data collection is collected, sent up to the cloud to the customer who ordered a calibration, and they get a data package back. Now, instead of running around in the field with a piece of Spectral and a spectral radiometer attached to their back, all they have to do is click a few things on their computer and they can get a NIST traceable world-class calibration with a data package back through the cloud. What's happening on the ground? This just gives you an idea of what the mirror turrets look like. Just for size and scale, this is a 3.5 meter target with 40 mirrors deployed in it. Each mirror has its own independently controllable cover. So we can deploy 1 mirror or we can deploy 40 mirrors. Each mirror bay can be different size or different numbers of mirrors behind there. And in doing so, we're able to actually serve different types of GSDs, like a UAV GSD, which has sub-centimeter GSD, can have some very small mirrors that we reveal. Or if we're doing a Landsat class calibration, we may need all 40 mirrors to generate enough signal in the SWIR channels for that particular satellite. So the other thing we can do with this is we can open, if the satellite can track us for a little bit and we can track them, then we can open up a successive number of mirrors. We can open up 20 mirrors, 10 mirrors, 5 mirrors, and give them a linear evaluation through an empirical line method that goes directly through the zero reflectance value, because when the mirrors are off, they're really off. We have very good control of that. And then also, we know exactly where the mirror positions are. So we give them precise sub-centimeter ground control points with each of these stations, so they can orthorectify their images at the same time they're doing radiometry and geometry. So it really is kind of a complete system and a complete calibration in one look. So this just shows the covers dropping off, the mirrors opening up. It finds the sun. We find the satellite. We act as a constant point source. This is an animation so that we're not actually flashing, we just look like a constant dot. And then we can track for a couple of seconds or up to a few minutes, depending on what the satellite's actually doing. We can track from horizon to horizon if we need to, but usually you only track about 20 degrees over the arc or 40 degrees over the arc, because otherwise the atmospheric burden becomes too high. We get too high of an atmospheric path. So the easiest way to think about this, and this harkens back to space telescopes and some of the other lectures that are coming up, is we are a traceable star on the ground, traceable adjustable star on the ground. Stars have been used for many decades as reference sources for telescopes for 2 reasons. One is radiance, and the other is geometric correction, because you know it's a point source. So at the same time, with what we're doing here is we're making a traceable star on the ground. We're using the sun as our star, and we're just relaying that to the satellite. So it's grounded in a lot of classic radiometry and classic optical astronomy techniques that have been used before, but now it's in an automated cloud access turret. So we can serve any GSD with this system. So this is the fully deployed FLAIR system. We have the customer who's requested a calibration through the portal. It activates our radiometric tower, and then we track the satellite if that's what they ordered today. Maybe they also ordered an airborne underflight. We can also provide a calibration for that by opening a different set of mirrors. And maybe even they have a UAV that's underflying that area because they're trying to get higher and higher resolution data about what's going on. We can handle all 3 of those within that single mirror turret array. The other thing we can handle is a lot of problems that are really difficult to tackle today with the current methodologies that are out there. So I won't spend too much time on any one of these, but there are papers to back up each one of these bullets. So low uncertainty calibration. We don't need a desert or a large tarp to lay down. We can take these systems and put them on top of mountaintops or on top of floating barges in the ocean. We can place them anywhere they need to. But when we put them on at top of mountains at high altitude, we're reducing the atmospheric burden. There's less atmosphere up there. Therefore, we may be getting factors of 2 or 3x better than current uncertainty calibrations today. And one of our next sites will actually be on top of Mauna Loa in Hawaii. And we're really excited about that. And so is NASA. We've been awarded a contract for SLIT, which is Landsat 9 and Landsat 8, and a new methodology that we're exploring for calibration for those devices. We're actually measuring the atmosphere when we do these measurements. We're measuring and extracting the atmosphere. And so that has potential to offer some atmospheric information and improve some of the methodologies out there today on each measurement. We don't need a completely clear sky. In a lot of the classic methodologies, you need a really, really clear sky to do these measurements. And with this, we can use partially cloudy days. Clouds don't bother us as long as we have a clear line of sight between the sun, the mirrors, and the satellite. We can put these sites anywhere they need to be. We can drop them on top of a building. We can drop them in a parking lot. We can drop them in a field, and they work. And that means we can also put them in unconventional locations. Like if I'm doing coral health down along the equatorial regions, I have very high atmosphere, but I have very low density of potential calibration sites down there. I can put a flare system down there and it can really do a great job of calibration. So it opens up some unconventional orbit thinking in terms of putting satellites down in places where we want to do some monitoring that hasn't been possible before. Spatial and spectral problems. I went on about PSF and MTF, point spread function, modulation transfer function. You get that with these point sources. We can get BRDF too. If you can track us and we can track you, we can extract BRDF from the scene by accessing a number of different angular images from the satellite. Again, there's a paper on that if you're interested in more of that, that has been demonstrated. We can introduce, the mirrors don't have to be monolithic. They can be different types of mirrors, including polarized mirrors. So now that doesn't exist today. The ability to get a calibrated polarized target is very, very difficult. We can offer polarization into these by simply polarizing the mirrors or putting polarized coatings on the mirrors. Or we can offer spectral signatures by putting specific band coatings on the materials. Again, on band materials on the mirrors. And as long, again, as they're sub-pixel, they look like a spectral signature. So we're creating characterized spectral signatures on the ground, which may be useful for multispectral and hyperspectral calibration. Also, the mirrors also work out into the mid-infrared, and I can't really talk too much about that. That is classified, but there is work being done out there. The mirrors do work out to 5 microns. And then another thing that we're looking at is optical fingerprinting. So with these mirrors, you can create some really interesting fundamental fiducial responses of the satellites, which are almost like fingerprints for the satellite. And if once you have that response, you can actually use that to figure out as you go forward in processing of the image and go backwards in processing the image, whether or not somebody tampered with the image, because you have the fundamental response of the satellite or the fingerprint of that satellite. So it makes them very hard to fake images out, and especially in the fake news image world that we live in today, or at least up to a couple of days ago we lived in. It's really important to make sure that we have the right set of information and that we can't be faked out. People can't fake these images out. So a lot of information there. I'm going to talk now about how we do geometric and radiometric calibration with FLAIR. This is part 4, and then we'll finish up with part 5. First, I just want to emphasize that, again, the access of this system, we build the network, we build the hardware. You don't purchase the hardware. All you do is you get a subscription to FLAIR, and you go to this calendar-based calibration system, and you select your satellite, select the calibration site, and we give you a window of opportunity where you can get a calibration within about a 10-day window. And it's as simple as that. And then as soon as that calibration is executed, we hand that back to you. Very simple, very easy, very potentially has the ability to lower the cost of these types of calibrations by factors, perhaps even an order of magnitude. We offer a variety of different services. We offer looks, which is the actual execution of the FLAIR system. So we offer just a spatial look. We're not taking radiometric data. We're just providing spatial information about the point source. Or we offer a radiometric look, which is the spatial and the radiometric information. We're not accessing your image. Your image is your image with the looks down here. But if you give us back the image, you want a traceable third-party analysis of that, of the spatial properties or the radiometric properties. If you give us back the image, again, through the portal, after you've taken the image, you give it back to us, we'll do the analysis for you, and we'll give you back a third-party traceable ARD ready calibration data set for your use if your team doesn't do the image processing themselves. So eval, and that's called an eval. So we have evals and we have looks. And this just gives you a little bit more of a graphical way to look at what types of products are derived from each of those types of services. So let's look at what an EVAL-S might look like. So here we took some images we got some images back from Sentinel 2B from ESA. And so this is a point source that was taken on July 1st, 7/1. This is one that was taken on July 11th, 7/11. And this is one that was taken on 731. You can see that just with a single image, we're actually able to, on this high quality telescope, develop a pretty good point source. But if we actually take them all together, if the customer gave us all 3 of these images, or they did the analysis with multiple images themselves, they would actually get this oversampled point spread function, which helps to statistically beat down the noise and increase the accuracy of that point spread function. So right away, either with a single image or with multiple images, we can start to generate point spread function or MTF information. If we need more information, like we talked about line targets, this is a line target for a 3-meter satellite that we were testing. This is the ground tarp that we were comparing to, some edge tarp and some line edge target and some line target and some point target equivalencies, just to make sure that these 3 methodologies jive to each other. So we can do these types of services on demand. This tarp took several days and some blood, sweat, and tears to create, and kept trying to blow away with the wind in New Hampshire. These mirror targets, Brandon and I were able to set these up in under an hour and take them down in less than 20 minutes. Really easy, really quick, very easy to do this type of testing. So this is just an image of that overpass. So here we see our line image. This is the true impulse line function with the same edge as this. This is the cross track, and this is the along track. We have the along track here. And so then we did some analysis just to make sure that these methods work. And there's a paper coming out soon from some of our colleagues and partners at RIT. They're going to be publishing at IGARS some more information about edge, line, and point source methodologies. Now, actually in these graphs, it's very hard to see, but there are actually edge and line and point source graphs in these lines. And you can see that they're almost indistinguishable from each other. And so the same set of information that you get from an edge, which is the classic way to do it, can be derived from a line or a point source function. So very powerful. The other nice thing is, again, these are omnidirectional. So here we care about the direction of travel. Here we don't, but we still get the same set of information. Let's talk about radiometric. So that's a look-S or an EVAL-S type evaluation. A look-R is we have 2 methods of traceability. We have a Langley method. For those of you uneducated there, it's you take the radiometer, you track the sun for a day. That day has to be nearly perfect atmosphere. You don't get them very often, especially in New Hampshire or South Dakota. You do get them quite often on top of Mauna Loa, so that's why we want to be there as well. It gives us the ability to know exactly what the sun is doing outside the atmosphere. We have an instrument called the TSIS-1, which is on the space station. Really nice instrument that NASA built, sub 1% absolute accuracy. So we know exactly what the sun is doing outside the atmosphere. What we're using is the radiometer tower inside the atmosphere to measure the atmosphere and actually develop that atmospheric burden. And these are what are called Langley peaks, these little red dots. We use that to develop a calibration curve that we then apply to our signal. This is done throughout the industry as a baseline for a lot of radiometric calibration, because it also gives you top of atmosphere, which we get from the TSIS-1. It gives us this surface reflectance, and it gives us the downwelling and the upwelling extraction. And actually the downwelling is derived, and we measure that, and the upwelling is projected back with Modtran. But since we have the downwelling, we're pretty sure we know exactly what the conditions are for the Modtran. It makes our Modtran much more accurate. But additionally, if we only had just the Langley plots, we'd only be able to calibrate on certain days at certain and X number of times per year. We really want to be able to do that all the time. So embedded in our radiometric tower is also an integrating sphere. So when the tower is retracted into its closed position, we are actually calibrating using an integrating sphere to make sure the baseline of that instrument stays constant. And also it helps to correct for some of these atmospheric squiggles that you see out here, atmospheric absorption lines. And you see that coming through in some of the traceability. This is an uncertainty analysis done with a Langley plot. We're about 3.5% until we get to the atmospheric lines. This just shows also how RadCalNet would present this, which is a calibration site that NASA maintains. So we get similar data to what they produce. The blue line is the actual measurement. The upper yellow and lower yellow lines are the upper and lower bounds of uncertainty on that, about 3.5%. But we also, our radiometric tower is not, is a spectral hyperspectral radiometric spectrometer, and it actually gives you 1 nanometer increment data, at least throughout the silicon range. And then in the SWIR, we also get some banded information, which I'll show in the next slide coming up. But what we're able to do then is, if you give us the images back and you tell us something about your satellite, your bands, your RSR, your relative spectral response of your bands, we can give you back calibration coefficients for each of those bands based on the radiometric extraction from the FLAIR image and our calibration system. So these are your absolute coefficients with error bounds on them. So the last section of my talk here is about calibration, ARD, and data value. And I'll talk first about ARD, but as you get the sense, FLAIR's mission is to provide a new tool to the radiometric community to be able to do these calibrations more in real time with less arduous effort and lower cost. We hope to be able to change the calibration fidelity, frequency, and value by doing that. There are a lot of people excited about this, and there are a lot of people working on this. So it's not just Labsphere trying to do this. The space agencies, the Committee for Earth Observation Science, if you want to know more, ceos.org is I think it's down today, but it may be up tomorrow. They are working on what's called analysis ready data, or ARD, and they've come out with a number of standards. The first one is CARD4L, CEOS analysis ready data for land. And that prescribes a methodology and a set of radiometric parameters and methods that enable you to take raw imagery to fully harmonized data sets, which allows your users who want to use the data to not worry about where the data came from, but be able to just use the data for what they want to get to. You've all heard the expression, data is the new oil. Well, if you want to drill for oil, you got to find out where the oil is. If you want to get the data, you actually have to know how that data was produced. So the analysis ready data is a big part of this. We're trying to stay in lockstep with the FLAIR effort, and everybody is pouring a lot of manpower into this. If you're interested more in what's going on in the ARD sectors, please let me know, because we are thinking about starting a new standard in that as well, in IEEE, as well as other organizations. So ARD basically requires radiometry, calibration, and atmospheric correction. It requires a really good knowledge of what that satellite can do from its image quality perspective, and it needs you to register to the image to the planet very accurately. We want to extract out the good data and give you all of the parameterization that the satellite can do, so you know how it was collected. We want to take out the bad data, like the clouds, spurious data that might have been generated, or instrument artifacts. Ultimately, we want to pull out the instrument artifacts by giving you good metadata. We want interoperability. We want to be able to normalize between sensors, and we want to offer potentially a method that everybody can use, regardless of the size of the pixels on the ground. Ultimately, also, if you have the ARD components, you're able to reduce the image to what the customer wants. They don't want to sort through petabytes of information to be able to get to this inference. They want the lake with the algae bloom on it, or they want the count the cars in the parking lot at Target. They don't want to sift through the image to get it. They just want to get to the data to get the insight that they get from the data. Just also, if you're interested in ARD as well, there's some good resources here at Planet, which is a big satellite provider, commercial data imagery provider, and you can see their top of Atmosphere versus their ARD product. There's quite a difference between those two. And additionally, it enables data extraction and sensor fusion. If we can get the data right at the first pixel, then we can start to harmonize these sensor fleets. The idea of launching hundreds of satellites is not to have hundreds of different images. The idea is to have one image of the Earth taken every day, all the time, meaning that those hundreds of satellites act like one camera, or a movie camera of the Earth. We want to be able to harmonize that. If you have hundreds of satellites and they've all been up for different periods of time, these things change on orbit. You have to have some way to harmonize those within the fleet. Or you want to harmonize across platforms. You don't just want what's within the constellation, you want to harmonize it to other satellites, or small satellites, or UAVs, or other things. or you want to fuse it with other data products like SAR, synthetic aperture radar, which can see through clouds and gives you other information. And you want to create what are called virtual constellations. And that requires being able to harmonize a variety of different satellites and data sets together to create these virtual sort of mega imagers. And then ultimately, if you get all this right, that a lot of people are using machine learning and artificial intelligence to extract data from these, because you're getting petabytes of information now from some of these systems every single day. No human being can sort through that. So we're using ML and AI, and they're great. And I'm a big fan of ML and AI myself. But if you don't feed good information into these algorithms, you don't get good insight or value out of those learnings. So as the old expression goes, garbage in, garbage out. If we don't put good data in from the first pixel, no matter how good our ML or AI is, it could be better if we put in better data. And then we also want to harmonize across different levels. Level 0 is kind of raw data. Level 4 is fully fused, harmonized data. And we want to be able to use FLAIR across all of these types of things, or have analysis ready data at any level here that the customer wants to access it. So FLAIR does that by basically giving the opportunity to see these point sources with different satellites, different points of the Earth. You're always going to get radiometric information. You're always going to get spatial information. Once you have the different imagers and their different spatial responses, and the imagers and their different spectral responses, then you can pin those all together into responses that you can normalize out to each other, and ultimately you can fuse them into the data product that you really want to get. So the information is here between the 3 fused products, and FLAIR was the thing that enabled us to tie these 3 different satellites together into one data set that is continuous, traceable, and provides excellent information for our utility. It unlocks the value of ARD. It helps us get to surface reflectance. It provides a stable radiometric traceable source for any GSD. It allows us to harmonize between different types of electro-optical constellations and architectures. And ultimately, once we have all of that and we know our satellites are working right, now we can start to look at time series or change detection over time. Something is changing over time. We want to determine that. If the satellite's changing over time, that messes that all up. But if we know the baseline for the satellite, we can start to do that. Or we can do monitoring or diagnostic efforts on the satellites if they're having problems, or we can optimize our machine learning or our AI results by giving them better data to work with. And then another local tie-in, we've been doing a lot of work with MIT as well, the Astro Aero group under Ali DeWerk and Afreen Siddiq. And they have been doing some wonderful work, if you're interested, in terms of trying to correlate data value back to calibration. So if you have data and you use it, it gives you a certain amount of extraction capability. If your data was more accurate, how much more value do you get out of that? And they built some wonderful models, including some decision trees that allow you to determine at what point in time do I have return on investment for better calibration for my better data and giving that data back to my customers. So they've been a great partner throughout this entire process. And we really enjoy working with them and staying local in the area here. So with that, just to wrap it all up, FLAIR provides all satellite calibration artifacts in a single event. It is the only technology that can do that currently. It gives you spatial, radiometric, and ground registration. And it really provides you with all the things you need for image quality, for machine learning and artificial intelligence. It enables you to test with the world in the loop, to be able to include the atmosphere, to have a point source, to have an impulse response function, and calibrate all types of different assets with the same type of calibration device. It's a service. It's not a hardware purchase. We hope that makes it faster, lower cost, and available on demand. So you use it as much as you need it, when you need it. And then the network is active and ready to go. We're currently serving commercial partners and government partners as well with this type of calibration and building that the fiducials of this. We are proving out, it takes a long time to prove to this community that these things work, but I think we're on the right track towards really baselining ourselves against the existing methodologies that are out there. And hopefully we plan to, in the future, as we learn more and get better at this, actually supersede them and provide better data to this. And then ultimately, again, heart of hearts here, calibration is vital to extracting more information from satellite data. People want better information, they want more information, but we're really all about getting it right from the first pixel and enabling that next generation of Earth observation, climatology, science, and data information that people can use for the insights that this particular technology has unique capability to present to the world. So with that, that is my last slide, and this is how you can reach us. If you have more questions, and at this point, I'll take any verbal questions if we have any, Brandon.
Yeah, that's great, Chris. Thanks. Take a breath.
I'm just typing out some questions here. Actually, I have a couple of questions that just came in that I was going to type an answer to, but I might as well just answer now. How many sites are online or planned? At the moment, we have full function sites in South Dakota and in Texas. We have a smaller station. It's currently sitting in New Hampshire. It's going to be shipped to Texas soon as part of a multi-array experiment. The next station that we're planning on developing is going to be going to the top of Mauna Loa in Hawaii. And then after that, we have 7 or 8 sites that are kind of in consideration and active planning. But the speed at which we develop the network is going to be kind of depending on
organic
demand
funding.
And on, was it?
Organic funding.
Yeah, organic funding, and finding good partnerships. You know, a lot of this we do with universities or government agencies, and if we find the right person, then we can select a site and put it there. But we're looking to have these hopefully just globally distributed, so you don't have worries about, okay, if this station's socked in with clouds, you can on the next orbit you can get one somewhere else. Northern and southern hemisphere.
Northern and southern hemispheres, so we're not seasonality.
Climate types. Yeah.
Right. Yep.
Let's see. And then next is how do you decide where to place these systems, especially at very remote sites? Well, we want to be distributed, but there's also how many days a year of sunshine do you get? Because while it's true we don't need to be, we need only a small fraction of clear sky, we still can't be clouded over. It's the type of background, we want very large, dark targets. So we can use agricultural fields, we can use very big parking lots, but if we're trying to look at a 30-meter pixel, now you have to get something, you need a few pixels either side. So it has to be very large. That's one of the reasons we're going to the top of Mauna Loa, because lava flows are nice and dark and they are kind of Lambertian, and it is just an entire mountainside that's a wonderful calibration target. So,
right. More questions?
Yes. So how do you keep these stations clean?
Right. Good question. So if you see the naked mirrors here, those are obviously manually maintained and cleaned. But
by that guy down at the bottom right in that photo, that's it. We have a lot of manual work, but the automated stations have covers so those black covers that you see on there are really tight seal that prevents dirt and debris from getting in. And the mirrors are only open for really a few seconds to a few minutes at a time, and then they're covered back up. We are going to be, we're working on our maintenance schedule, but it's probably twice a year these systems need to be maintained, depending on local conditions. And as we do that, we clean them and inspect them. But we can also actively measure the mirrors with the solar radiometer. So we know what the reflectance is supposed to be, and we measure the sun, and then we can measure the mirror. And if there's any obvious degradation in that signal, then we can shut off that mirror or actively clean it.
Yeah, there's also a laminar flow.
One of the systems has the laminar flow.
Right, and having local partners is also super helpful. So we like to develop this in partnership with people that might be in proximity in case we do get some schmutz on one of the mirrors. They can go wipe it off for us. universities and or local partners or government partners are essential to some of our maintenance schemes. But as Brandon said, a couple times a year, we do have to go out and service.
I'm just thinking about birds and animals.
Bird fouling.
That's
critters.
been
Quite
a bit of discussion.
We had a bird's nest built in our calibration station. That was interesting.
That did happen at one point. But with each time we learn, we redesign it, make it harder for things to get in it, and we better seal the systems. The mirrors are only open for a short amount of time, but it is still possible that something could be attracted to that potentially. So,
yeah, we're considering some ocean sites, and there we're worried about ocean spray and other types of things that could be a lot more aggressive in terms of the cleaning system we have to.
You get
implement.
Pollen during certain seasons. And
pollen.
We do have a camera on the system that if it's obvious that there's a dust storm or something, then we can shut it down.
And we have survived at least one mini tornado. So these are pretty robust, and several snowstorms as well.
That's great. Any other questions? If somebody has a question, just pipe up, unmute yourself. And
is there any existing network to sort of retrieve, at the ground radiance data? Kind of a part of the system here. To just get the data, but not send the light back up to a satellite.
Yes, so we can do that. We have a radiometer. Our hyperspectral radiometer, which is it's a sort of a development of existing networks, because that type of network exists. It's NASA's Aeronet federated system has these sorts of monitoring systems all over the world. And there are also a couple of Vicarious instrumented sites that are based on the large deserts that do that same measurement. We actually haven't offered that as part of our as a product that you can just order just that data. But, it's something we've been willing to explore, and we're collecting the data, we're archiving it. And one of the ways we've thought about working with certain agencies is if we have access to an area, then we can make the data available publicly.
Yeah, I wasn't even aware if there was any existing networks. It's interesting that.
There's RadCalNet. Yeah, so RadCalNet is an instrumented series of sites around the world maintained by NASA and the space agencies where the ground is actually measured, and these are the current calibration sites that are out there.
These are big open areas, deserts, gravel fields, that kind of a thing. But there's only a handful of them anywhere in the world.
Right.
And they change a lot more than a mirror,
right,
as you might imagine.
Yeah, a little bit of rain and those sites can be down for weeks.
Wow. Would it be useful for you to set up at one of those sites to get a comparison?
Yeah, absolutely.
Yes, we're trying to work that. We have some planning for that, actually.
So I'm going back up to my friend Mark here.
Yep.
This is Railroad Valley.
We're trying to get a site there.
We are trying. That is one of our future sites, we hope. It can be challenging to get some of these permits at some of these locations, but that is one we have on target, because Railroad Valley is probably the premier RadCalNet site, and NASA wants us to be there too, because this is what they call big pixel targets. Big, huge areas, and a lot of the high res sats don't really benefit from that, because it doesn't give them a lot of information about what's going on with the imager itself. It just gives them this big white amorphous target. But if you had both the flare target and the big white amorphous target side by side, you could make that immediate comparison between spatial resolution and the big pixel target classic methodology. So yes, we'd love to be at these already well characterized sites. So there's also one-to-one correspondence between what we're reporting and what NASA's reporting.
Wow. So in a place like that, the desert floor's reflectance doesn't change with seasons, or
it doesn't.
It does.
Yeah.
Well, it doesn't. It doesn't. It doesn't change a huge amount, but sometimes you get snow. It does actually snow there, and then it changes massively.
Well, yeah.
And if you get some rain, then that changes. There are other sites in the world where actually that they use dunes. Like this is a baked out alkali flat, so it's one of the most stable, but it's only one. There are other places that are dunes, and actually the structure of the dunes, you get these shadows and things that over 30 meters, it might be pretty well averaged, but over 2 meters, it's dramatically different.
Right. So a high res
There's sites that
sat,
have vegetation too that do change frequently.
a big pixel site can use that, but a high res sat couldn't use that. But there are other sites that are used. One of the techniques that South Dakota State uses, for example, is called pseudo invariant calibration sites, or PIC sites. And that's basically a really fancy way of saying big deserts around the world that they've identified that don't change very much. They're not actively measured, but they're pretty stable. So if Landsat flies over them and you fly over that same site and you take a picture of it, you can compare yourself to Landsat. So it's not an absolute reference, but it is a relativistic reference.
On this particular slide, did you mention what all those smaller, I don't know, round targets are scattered around?
Oh, you mean these little things right here?
Yeah.
Yeah, those are cinder blocks.
Okay.
High tech, duct tape and cinder blocks.
We use roofing nails for our big tarp in the backyard. In the back lot.
Yeah, wind. There's a good story here with these are 20-meter tarps. I've seen grad students fly off with these tarps when the wind picks up. If they forget to let go, they will get airborne.
Wow.
That's why it's called Aladdin.
Field work.
Yeah, flying carpets is not the way you want to go for calibration events.
Do you guys produce coatings for fabrics as well, or not?
We do have a flexible coating that we can use. Yes. And we have a spray coating called Permaflect, and there's a flexible version of that, which can actually is solder permanent, so it actually can be just left out in the field permanently, and just occasionally dusted off and cleaned off with a hose. So we do that too. I mean, like I said, I'm talking about mirror targets. We love Lambertian targets. Don't get us wrong. We do that a lot, but the mirror targets do have some advantages to them.
Well, I can see how you'd need to involve hundreds of people in the standards process because you've got all these different organizations using the same methods, right?
Well, so like Landsat 8 and Sentinel 2, which are two of the best satellites in the world and are supposed to be really closely matched together. There's a team of hundreds of people that have spent years trying to harmonize those two satellites. And
they're still off by a few percent.
And they're still off by a few percent. So, and there's, I'm not meaning to degrade that work. It's vital work that they're doing, but obviously we have to do a little better than that if we're going to get to some of the real value in the data sets that people want. And especially if we're going to get to one of my former talks that David alluded to at the beginning is I gave a talk about environmental change and climate change analysis and the challenge that NASA has thrown down of getting 2%, now 1% on orbit for more than 25 years to really develop a climate prediction model. And this FLAIR is a step in the right direction, as well as other technologies like measuring the moon and other types of Vicarious. I didn't mention the moon calibrations, but there's a lot of other methods that people are trying to deploy. The more methods you have, the more ways you have to beat down the statistical noise and your uncertainty. And to get to 1% on orbit for 25 years, we're going to need every single one of those methodologies to develop a climate model that actually has predictive power.
Well, that's terrific. Well, thank you both very much, Chris and Brandon. Really appreciate it. It was a great talk. It's a really interesting topic.
Thank you.
And
welcome.
If there are no more questions, I guess we'll let you go.